Hello, in this video we're doing a little bit of mechanics review. Mechanics, Unit A is the most important unit to really know in physics as you're getting ready for the IB exams and in general. This is kind of the foundational stuff that a lot of different things build on. And should you find yourself taking some college physics, you are for sure going to focus on mechanics in like an intro college physics class. So in this, I'm going to go over two of the biggest kind of concepts in mechanics, two methods you use a lot to solve problems, and two of the ones that are a little sometimes trickier to use than, say, like using the Suvat equations. We're going to look at how you deal with forces and how you use conservation laws. Conservation of momentum and energy are really big. So here we go. Okay, one forces thing you do want to know is you want to know Newton's laws. They love to ask you about Newton's laws. They'll sometimes just ask you to state them. Here they are. Make sure you can say these. Translational equilibrium is a key word for the first law. The second law, remember, is not F equals ma, even though pretty much everybody else in the world says so. The IB is very finicky, as they like to be, and say, well, technically, Newton's second law is this equation. The net force on a thing is equal to its rate of change of momentum. And remember, if mass is constant, then this turns into ma, right? But that's like a special case officially when you have a constant m. But that's Newton's second law, so remember that's how they want you to say it, and it's useful sometimes to do change of momentum stuff. And Newton's third law is tricky. It's you have to do this. If you have a question about Newton's third law, about like what forces equal and opposite, about an action-reaction pair, you must think of it. Force of A on B equals negative force of B on A. However much thing A pushes on thing B will push back on A the same amount in the opposite direction. Remember, to define a force, there must be two objects. If you can't name the two objects, you're not talking about a force. There's like a ball rolling and you find yourself saying something like the force of the ball, that's not a thing. So there's always two things, pushing, pulling, when you're talking about forces, right? So here's one to try. Let's say you got a tire swing hanging from a rope. There's a rope holding the tire up with a tension force of 20 pounds. Pounds is a unit of force. The IB usually won't use it, but that's a good one to think about. What force must be equal and opposite to this tension force by Newton's third law? What do you think? What would you write? Take a moment, take a crack at it. If you said gravity, you would be wrong. It's not gravity because I could come cut that cord and then tension would definitely not equal gravity anymore. Newton's third law is always true, and it's about two objects. So what's the force of tension? It's the force of the rope pulling up on the tire. The opposite force must be the tire pulling down on the rope. That is the force equal to tension. It's different than what you're used to, where we're looking at all the forces on one object. We're looking at two forces on two different objects in a Newton's third law pair, which is part of the confusing part. Okay, but these two forces are always the same size. If I come sit in the tire, both of those forces increase a whole lot by the same amount. The tire doesn't get any heavier though, right? If you want to do gravity, what force would be equal and opposite to the force of gravity pulling down on the tire? Try that. Well, hopefully you said something like it would be the force of the tire pulling up on the earth. And it's true, the tire pulls up on the earth. Okay, because remember, gravity is the planet Earth pulling down on you with all of its mass. So this is Earth on tire. The Earth pulls the tire down. If the tire is about 20 pounds, let's say, the Earth pulls the tire down, 20 pounds of force. The tire pulls up on the Earth with 20 pounds of force. It's true. Those forces are equal and opposite because, like lug, they're both the same size. Yeah. Just 20 pounds to the Earth doesn't mean very much for the whole big giant Earth, but 20 pounds to a tire will make it like fall and stuff if you cut the string. Okay, so always do A on B, B on A for Newton's third law. You will screw them up otherwise because you're used to thinking about balanced forces on one object, which is great, just not for Newton's third law. Okay, the other thing, in the data booklet, they say F equals ma. If you think the F means force, you are in trouble. That is not good enough for the IB exams, definitely. It means net force, right? We need to know that that means net force, the sum of all of the forces, and officially like in one dimension at a time. So like all vector stuff, you really want to break it up and make sure you're only dealing with X stuff or Y stuff at any given time when you're mathing. So remember, you need to draw a free body diagram. If you're going to use F equals MA, you need an FBD, or you're just kind of giving up on the problem if you try to do it without one. Make sure you make an FBD if you're going to use F equals MA, and make sure you're thinking about the sum of the forces. That's really, really big. And you need to break any angled vectors up into components then. If you have like a force at an angle or the whole problem's on an angle, like on a ramp, you need to get it so that you can deal with like just the X stuff or just the Y stuff. Okay, let's look at one and see if we can see why this gets sticky. You try this. This is an IB paper 1 problem, a classic 8 kilogram thing falling through the air. We're given a drag force 60 newtons. What's the acceleration of the object? Go ahead, give it a shot. What did you get? Okay, here's the trap. Here's what they want you to do, or they're checking if you do this, because this would be wrong. You were like, oh, F equals ma. Force equals mass times acceleration. They gave me a force. They gave me a mass. I should be able to divide them and get the acceleration, right? No, no way. That's terrible. That's not what F equals ma means at all. The way to do it is to know that F means net force. So you're like, okay, I am going to make an FBD because I'm a good physics student. And I like to think about what's going on to understand the problem. And this is what's happening if a thing is falling. A drag force is like a force, you know, if you're falling downwards, drag force is resistive force. It's opposite the way you're moving. Why are you moving that way in the first place, though? Oh, yeah, there's this other force, gravity. Yeah, the force due to gravity is equal to m times little g. Acceleration due to gravity. Remember, none of those things are just called gravity. And g is about 10, especially on a paper 1. You can definitely do that. So, okay, Fg is about 80 newtons down. I got about 60 newtons up of drag force. So the net force would be 20 newtons. Really, negative 20 newtons. So I got to sum the forces to get a total force of 20 newtons down. The total force is what I divide by m to find my acceleration. Okay, so it's really, really important that you know F doesn't just mean force, it means net force. You have to draw a free body diagram if you're doing F equals ma. Speaking of fun versions of F equals ma, the IB and physics teachers everywhere love a box on a ramp, an inclined plane. It's a beautiful problem. You really want to know the trick to doing this of tilting your axes. So you want to do this whole crazy, let's just do parallel to the plane and perpendicular to the plane. So let's say X is like up and down the plane and Y is this way. You can do that. That's allowed. Nothing special about pure horizontal, pure vertical, math-wise. So let's call this X, let's call this Y, because then I'm accelerating along the X-axis. If there's like friction or something, that's also on the X-axis. And so everything is like on axis now, except for the weight vector, which remember is slang for force due to gravity. So you need to know how to break this weight vector up into pieces and how to do this angled thing. Here's what the triangle looks like. Make sure you can do this, practice doing this, memorize doing this. The deal is you have like a little similar right triangle situation here. So this angle is always equal to the angle of your ramp. And so we can SOHCAHTOA. There's the opposite side. There's the adjacent side, which means it's going to look like this. You really want to be able to do this right away. These are worth memorizing or practicing this triangle enough that you can do it super quick, because they want you to do it super quick, especially like on a paper 1 question. So the X component, in other words, a component parallel to the ramp, is the weight times the sine of the angle, because it's the opposite side here. And remember, weight is mg. So the hypotenuse of this triangle is mg big, right? That's the actual force pulling down on the thing. How much of that is this way? Well, you multiply the hypotenuse by the sine of the angle. How much of that is this way? Well, you multiply hypotenuse by the cosine. And bing, bang, boom, you got yourself your X and Y components of gravity on a ramp. Make sure you can do those, pretty quick. And remember, notice here is a great example of where the normal force does not equal the weight of the thing. That's not a thing. That's not a rule. It happens a lot, so you get used to it and get kind of sloppy. But don't assume R equals the weight. It's definitely not the case here, right? In this case, if there's nothing else happening in our weird y-axis, the normal force would be the same size as like the y component of your weight. Yeah, so normally, on a ramp, the normal force equals that big. But again, even that, like, don't take anything for 100%. There's no formula for the normal force. You got to always draw an FBD and do like a net force equals MA situation to figure out the normal force. Okay, new this year, there are so many force equations in the data booklet that are super handy. You do want to know, what all of these mean. Remember, your bare minimum prep here is like you got to know what every letter in the data booklet means and what each equation is for. So you definitely got to know, like, oh, FB is this like buoyancy force thing. So sometimes they might throw this at you. You got to know, like, big V is specifically the volume of the fluid that you're displacing. Is it some crazy principle like the buoyancy force is equal to the weight of the water that you displace, or fluid, whatever? So make sure you know what all of these are for, but these are formulas for individual forces, and almost all of them only give you magnitude is how you want to think of it. It just tells you how big the drag force is. Like, you double how fast you're going through a thick liquid, you'll double the drag force. So they tell you like the size of most forces. The one exception is Hooke's law, because of the negative sign here, kind of does give you vectors officially. But for the most part, think of these as telling you how big the forces are. But if you're doing any math with them, you want to make, guess what? A free body diagram. Because if there's a buoyancy force, there's for sure some other stuff happening, like probably gravity and who knows what else. Maybe both buoyancy and drag if it's like underwater and moving. That's fun, right? So as always, you got to draw all of the forces acting on the object. All these equations are for is telling you how big certain arrows on your diagram are, right? If it's moving through a liquid and there's a drag force, this equation will tell you how big your drag force arrow is. But you need to draw them, think about all the forces happening whenever you're doing force stuff. Some other random force stuff, remember, a common thing is they'll give you like a constant speed situation. If something's moving at a constant speed, it's not accelerating, so the net force is 0. That's a good one. Even, your brain doesn't like that, because if something's moving and the net force is 0, you're like, well, how's it even moving? Newton's first law, if it's in motion, it's going to stay in motion unless there's a net force. All right, so if you see the word equilibrium or constant speed, that's a thing to jump to. Acceleration equals 0, net force equals 0. See if that can get you somewhere. And a specific type of net force is a centripetal force. If you have a circular motion situation, remember that's what these equations are for. You still do F equals ma. It's just now A is V squared over R if you're moving in a circle. And the direction's a little weird. We do the direction where towards the center of the circle is positive and away from the center of the circle is negative. Makes everything kind of work out nice. So here's an example one. They like this, the dip in the road, where you got a normal force and a weight on you, say, as you drive through a dip in the road. You've probably noticed this driving. If you go kind of quick through a little dip, you feel heavy for a second, because the force you think of as your weight is what you actually feel is the normal force, the chair pushing up on your butt. Okay, so like here, if you're moving along a little circular section, we would call this a momentary circular motion we could get away with. And so the normal force is towards the center of this sort of big circle you're, for the moment, moving in. Your weight, the force due to gravity, is away. So we would do some of our forces like this. And that is equal to ma, where a is v squared over r. So here's another example where the normal force doesn't equal your weight. It equals your weight plus some stuff. The faster you go, the heavier you feel. And remember, if you got like the car on the top of the road or something, it's the opposite. But in this case, if you're moving in a circle like this, gravity is towards the center. So in this case, gravity we would math as positive, because we're saying for circular motion towards the center is positive, away from the center is negative. So kind of the opposite happens if you're going over a hill versus through the dip in the road. Okay, so that's some forces stuff. Again, another common thing to use a really good tool to solve lots of mechanicsy problems is conservation laws, conservation of energy and conservation of momentum. There's a lot of overlap between them. You kind of see both of them quite often. So if you are having a situation where you can't use F equals ma, or your dear old friend suvat, which everybody loves and tries to use on everything, remember, like, you can't use suvat if the acceleration isn't constant. Those equations are derived from like a linear velocity equation where acceleration is constant. So if it's like kind of complicated and stuff is happening in the middle and you got to clear before and after, doing a conservation of energy or conservation of momentum is a great method. Conservation of energy, you want to ask yourselves these questions. You need to look at the before and after and make a sketch of the before and after situations. So kind of two sketches so you can visualize what's happening. And you need to think about what these energies like mean. So don't fall into the trap of being like, oh, if it doesn't have kinetic energy, then it must have potential. That's not a thing. The rules are just this. What does kinetic energy mean? If something's moving, it's got kinetic energy. If something is up above the ground is usually how we deal with these in like a, simple, not in space kind of mechanics problem. If it's up above the ground, then it's got potential energy. And remember, we have an elastic potential energy. So is there any kind of spring happening? Is there a box pressed up against a spring? If so, you got your elastic potential energy. And so this is a great equation to use. This equation is a version of the most important definition to ever know in physics, which is what work is. Work is the change in energy, final minus initial. So a lot of times you do something like this. If no work is done, if there's no friction or anything, and you're assuming like energy is perfectly conserved and none leaves the system, and this is 0, then you just have your initial energy equals final energy situation. And just remember, this means add up all the energy of anything in your system at the beginning. So if there's anything moving, you're going to add a little kinetic energy term in here. If something's up off the ground, you're going to also add potential energy. If something's compressed against a spring, you'll add elastic potential. And then you do it all over again at the end. So always go to these questions if you're trying to do energy stuff. And again, like, general physics rule is picture the physical situation, sketch it out. Think conceptually about what's going on, why you have energy, where it's going. Is there work? Is there any energy coming into the system or leaving the system? You can account for that with this. That's the idea with conservation of energy. You can also do conservation of momentum. If you see the word collision, you should do conservation of momentum. That is a big hint. If there's a collision, you are definitely going to start by trying initial momentum equals final momentum. Is almost always how you do like a collision problem. So momentum is conserved in a collision because all your forces are internal. Remember, the deal according to Newton's second law is unless there's a net force, momentum doesn't change. And if there is a net force, momentum changes at this rate. Okay. But if you see collision, you're going to do conservation of momentum. We'll look at one of those in a second. Remember also your definitions of elastic and inelastic. In an elastic collision, kinetic energy is also conserved. So you have the same amount of kinetic energy before and after. Not just like conservation of energy in general, but specifically kinetic energy is conserved. If it's inelastic, you lose kinetic energy. And so you can't do like initial kinetic equals final kinetic. You can only do conservation of momentum. So momentum is conserved more often than kinetic energy is conserved. And remember, you're always talking about all the objects in a system. If you're doing a conservation kind of problem, you're almost definitely dealing with, usually, pretty often, I guess I'll say, you're usually dealing with more than one object. Momentum especially, so make sure you're like adding up the momentums of each thing. or the energy of all the different objects that you're like accounting for. Okay, so last, here's an old paper 2 question that we can try that's got a little bit of both momentum and energy stuff going on in it. So let's just look at how this would go. Feel free, pause the video, try this out, see if you can earn these 4 marks. Okay, let's see how you did. These would be great 4 marks to go for. These are, there's going to be questions on like electromagnetic induction and flux and Lenz's law and stuff, also worth 4 points. You want to spend your time on these 4 points because you can get these 4 points. Let's try to get them. Okay, the thing that would catch my eye when I'm looking at this is the word collision. Oops. Is the word collision. It's a collision, so I'm going to do conservation of momentum stuff. Yeah, so I'm going to do initial momentum equals final momentum. That's our conservation of momentum equation. That's not like a data booklet equation. That's just our brain going, oh, it's a collision. You have the same amount of energy or momentum before and after. And since it's a collision problem, I'm going to draw a sketch. I'm going to draw before and after. Okay, so I've just made a sketch here of the situation with my before and after, because if I'm going to do initial momentum equals final momentum, I got to picture what's happening in my initial situation and my final situation. Okay, so we want to calculate V. Again, collision, find the speed. That's definitely an initial equals final momentum thing. So I need to add the total momentum at the beginning and set it equal to the total momentum at the end. So remember, our equation for momentum is mass times velocity. That's the definition of momentum. It's a math definition. So I would want to show what I'm doing is I'm going to take m times v at the beginning. I'll use u for initial velocity, like in our Suvet equations. You could use vi if you prefer. Potato, potato. Times m times u y. And that's going to equal the total momentum at the end. This seems like an inelastic collision, a totally inelastic collision where the 2 trucks stick together. The trick in a totally inelastic collision is the 2 things, treat them as one big mass. Yeah, it's like one big mass now. That's like, 10,000 total kilograms. And they're moving together at some speed. So you don't have 2 separate velocities at the end. They're the same. Okay, some little simplifying I can do because I know this one starts from rest. That's 0. So I'm just going to jump to this then. V would be m times u for car X in the beginning divided by the total mass. That's all. And so we want to show the values we're putting in. And our answer will kind of get a mark for each sort of step. Okay, so I had 3,700 kilograms times 4 meters per second. I divide that by the total mass of 10,000 kilograms. And I get 1.48 meters per second. All of my answers here are, or given values here are 2 sig figs. So I should officially round my answer to 2 sig figs. All right, there you go. Now for 2, determine the kinetic energy lost as a result of the collision. This is a energy thing. And we can think about what's happening here, just for thinking about its sake. Is work is being done, probably, well, by friction and heat and sound and such, for the carts to stick together in the first place. Yeah, so I can figure out how much kinetic energy did I lose. I want to find the change, in other words, which is kind of the work on my system. So I'm going to do final minus initial energy, where I just take the kinetic energy at the end and take away the kinetic energy at the beginning. Again, picture what's going on. What is happening here kinetic energy-wise? I got a big mass moving at, I know now, 1.5 meters per second. What was happening at the beginning? This had no kinetic energy. This has some kinetic energy. And all I want to do is take the difference. So let's do that. I just want to do 1/2 times the total mass. That's my final energy. Minus 1/2 times just X had energy here before. If Y was moving, I would also put that here and take away the energy that Y had too. Like I would get my total initial energy. but y had none, so I don't need to do that. Okay, that's really it to find the change in energy. So let's just do it, put in the numbers and see what we get. So I'm going to do half of 10,000 times 1.5 squared. Often just like use the number from before, even if you rounded it, is usually fine because that's kind of how they make the mark schemes. You should be okay if you use the unrounded answer as well. I think things will round a little differently here at the end. But either one will be, generally speaking, okay. Okay, so this times, we were going 4 meters per second at the beginning. We're going to square that. I have way less, square this. I have way less kinetic energy at the end than I had at the beginning. When I subtract these, I'll find the difference is 18,000-ish joules. And best to always write scientific notation. Especially when I'm rounding and stuff. So I'm showing that this is definitely 2 sig figs. Okay, so there you go. That is a little example problem with some momentum and energy. But net forces, conservation laws are really big mechanics things to master and feel good about walking into the exams. So go practice some. Have fun.